Okay, we're going to continue on here. We've been talking chapter 16. Why not? Sounds good. We talked about acids and bases in this chapter. And remember that your basic sort of definition of an acid is something that has the ability to produce H plus ions in solution. Remember, in acid-base chemistry, H3O plus, which is the hydronium ion, and H plus are pretty much interchangeable. They really do just represent sort of the acid part of the solution. A base is something that has the ability to produce hydroxide. And in each of these cases, what we're talking about, for example, for an acid, is the ability to produce free floating H pluses or H3O pluses in solution, and also for a base to be able to produce hydroxide ions. Again, free floating in the solution. The relationship of hydroxide to H plus in a particular solution will determine whether or not it is acidic, basic, or neutral. A more really general definition of acid and bases that most people oftentimes will use is the Bronsted-Lowry definition. And the Bronsted-Lowry definition, an acid is a proton donor. So it's somebody that will give away an H plus, while a base is a proton acceptor. Remember that as we talked about there, the plus part of it is also really important because when somebody does lose an H plus, it's not just a hydrogen, but their sign will change as well, or their charge will change as well, because they're one less positive, which means that you become one more negative when you kind of lose a positive guy. And also somebody should gain an H plus, they will become one more positive because they're gaining that plus. So you want to make sure that you do adjust the charges on everything when somebody gains or loses an electron. And sort of the consequence of Bronsted-Lowry is we have an acid and base on the left-hand side of an equation, and they do form partners on the other side, which is, say, the conjugate acid and the conjugate base. And remember that really what's happening here is our acid is donating the H plus over. So the acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other side. Remember, in order for them to be pairs, that is the absolute only difference that there should be, is that one H plus. So when we go from the acid to the conjugate base, we'll have one less H plus. And when we go from the base to the conjugate acid, it will have one more H plus as it gains it. And that creates our acid conjugate base pairs. So for example here, I'll do water, I guess. HCl plus some water. In this case, our HCl would act as an acid. Our water will act as a base. And it will accept the H plus. And it will make H3O plus and Cl minus. This being the acid, which is related to this, which is our conjugate base. And that being the base is related to our conjugate acid in this particular case. Again, the only difference between those two guys is that one H plus difference. As I mentioned last time, pretty much your run-of-the-mill acid and bases on the left-hand side of the arrow. All your conjugate partners on the right-hand side of the arrow is typically where you find those guys as well. We also talked about the idea that certain things can act as an acid or base, and that is what is known as being amphoteric. And water is actually an example of that. As we saw, water can act as an acid in certain situations, could also act as a base in certain situations. And that is what happens when water sort of gets together with other waters. One acts as an acid, one acts as a base. And that brings us to an important relationship of like water basically making H plus and OH minus. And this relationship was referred to as an equilibrium relationship. And it sets up what is known as Kw, which is the concentration of H plus times the concentration of OH minus. And that equals 1 times 10 to the minus 14. As we talked about last time, although in reality, because it is an equilibrium constant, it does change with temperature, but for the most part, and especially in this class, that's pretty much a number you should know, and it is going to be pretty much that number all the time. It can, in some cases, change, but pretty much 99.999% of the time, that's going to be the number that you're going to probably use for Kw. The reason we could use this is we could do really the same calculation regardless of what we're given. If we're given the base part of the solution, we could take 1 times 10 to the minus 14 and divide it by the hydroxide concentration. Or if we are given the H plus concentration, we could use 1 times 10 to the minus 14 and divide it by the H plus concentration. As we also talked about, it's really important in this chapter that you are using your exponent button. Otherwise, you will find yourself, off as you're doing your calculations. If we compare the H plus concentration and it is larger than the OH minus concentration, essentially the acid part of the solution is bigger than the base part of the solution, it will be acidic. If the H plus concentration is pretty much the same as the OH minus concentration, then they would both equal 1 times 10 to the minus 7, and they will be neutral. And if the OH minus concentration, which is the base part of the solution, is actually larger than the acid part of the solution, then the solution will be basic. So we could use that to sort of compare our concentrations and see if the solution should be acidic, basic, or neutral. Any questions on any of that stuff we talked about last time there? So I think we were right in the middle of an example, which was this one. And I think we did the very first one last time. So why don't you do the remaining 3? So we're looking for this first one, the OH minus concentration, and is it acidic, basic, or neutral? For the last 2, we're looking for the H plus concentration, and are they acidic, basic, or neutral? So take a few moments, grab your calculator, make sure you know how to properly punch these in and see what you come up with here. Yeah, let's take a look. So again, the good news is it's really the same calculation here. Whenever you're kind of given a concentration and you want the other concentration, you can use your KW, which is our H plus times our OH minus equals 1 times 10 to the minus 14. Again, a reminder that that is the same as saying H3O plus. So again, you could kind of interchange those guys if you want. Now, in this case, we have the OH minus, so we have the H plus, so the OH minus would equal 1 times 10 to the minus 14, which is that constant number you need to know, divided by our 2.6 times 10 to the minus 8. Once again, we want to make sure that we're using our exponent button here when we punch that in. And if you do that with your exponent button, you're going to get 3.8 times 10 to the minus 7. We do need a molarity on that since it is a concentration. Any questions on the calculation there? Now, at this point, we want to compare really the concentrations, and for the most part, you could actually just compare the exponent part of it. And in this case, which one is larger, the H plus or the OH minus? It's actually the OH minus here is going to be larger. It has the smaller negative exponent, so that means we're only going 7 places this way versus 8 places that way and putting zeros. So when you have a negative exponent, right, the smaller negative exponent is actually the larger number. So that would mean in this case, this is going to actually be basic. Any questions on that? And again, if you're not sure what I might be talking about there, that is kind of like the first guy in decimal form, and this would be the second guy in decimal form. More zeros here on this guy, right? So it's a much smaller number. Any questions on that one? Taking a look at the next one here, we do have the hydroxide concentration. So to solve for our H plus, we're going to do 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Once again, that's a 1 exponent button, negative button 14, divide 6.2 exponent button, negative button, and 9. Yeah, so again, that is how you should probably be punching it in. In this case, we will end up with 1.6 times 10 to the minus 6 molar. In this case, comparing the OH minus to our H plus concentration, it is actually in this one, the H plus concentration is larger than the OH minus concentration, which means this guy is going to be acidic. Yeah. Any questions on that one there? Same calculation here. So we're going to go H plus 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. That is going to get us here 1.2 times 10 to the minus 12 molar. And in comparison here, actually, is our hydroxide that is larger than our H plus, which means this guy should be basic. Yeah. Any questions on any of those calculations there? Once again, your calculator may not give you some of these answers in scientific notation, may be decimal form. You could turn it into scientific notation. Take a look at this one. It is our OH minus concentration, going to be our Kw divided by our H plus, which was given to us. So again, 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 5. We'll go with 3.6 times 10 to the minus 10. Again, it does need molarity there as it is a concentration. So upon comparison here, we do see that our H plus is going to be larger. So our H plus concentration is going to be larger than our OH minus, which means that should be acidic, right, in this particular case. Any questions on Kw, H plus, OH minus concentrations? Okay. Think we'll skip that one since it's kind of similar. The next thing we're going to actually talk about is the pH scale. And the pH scale is what we use to measure acidity. That's not negative. That's just from PowerPoint. So that is the pH equation. But the pH scale runs from 0 to 7 to 14. And below 7 to 0 is all right. And above 7 is basic. And at 7 there is technically neutral. At 7 is neutral because if you take the H plus concentration, OH minus concentration, and they equal each other, it technically will equal 1 times 10 to minus 7, which gives you a pH of 7 on the nose. As you go from 7 towards 14, that's going to be basic. As you go from 7 towards 0, that's going to be acidic. Or more acidic, I guess. That's the way to put that. More basic and more acidic in that case. For us, we are going to use kind of 7 on the nose as neutral. If it's anything up kind of above 7, will be slightly basic. Anything below 7 will be slightly acidic, unless it's like roundable, like, 6.999, it's pretty close to 7 or something like that. So we'll just kind of use that dead on as the neutral for 7. Our equation for pH, and by the way, it tells you what you need. pH means you need the H plus concentration. Negative log of the H plus concentration is how you calculate it. Now, this equation and all the rest of them we're going to talk about will depend on sort of the type of calculator you have, whether you have a display calculator or a non-display calculator. If you're not sure what type of calculator you have, you could just hit log, and if it says log on your screen, you have a display calculator. And if it says error on your screen or gives you like an error message, you have a non-display calculator. So you just hit log and it says log, you got a display calculator. And if you hit log and it gives you an error, then you have a non-display calculator. If you have a display calculator, this formula and all the other ones we're going to see, you pretty much type it in exactly the way it's written. You hit your negative button, not your subtract. You hit your log, and then you probably put your number in using your exponent button. Yeah. Now, if you have a non-display calculator, pretty much you always got to work backwards in all these calculations, which means you would have to start with a number. And again, probably using your exponent button there to punch it in properly. You then need to hit the log button, and then you need to hit the negative button. So you kind of have to work backwards. So pretty much display calculator, just like it's written. Non-display, you pretty much have to work on the backwards way, and usually always start with the number. So depending on which one you have, punch it in correctly, hopefully. So if we look at significant figures with pH, the rule is that if you calculate a value like pH, or POH, which we'll talk about shortly, the number of decimal places that you have in your pH value should equal the number of significant figures in the concentration. So we are going from significant figures to decimal places and backwards. So if you have decimal places in a pH to significant figures in a concentration. So we're going to talk about going both ways, but that is what we're talking about here. So why don't you try it here? If you have an H plus concentration, what would be the pH with the proper number of digits? So make sure you know how to punch it in and see what you get. Okay, so if you put it in, again, depending on your calculator, if you have a display, you would roll with the negative button, the log button, the 1, your exponent button, your negative button, and 5. If you have a non-display, you would punch it in with 1 exponent button, negative button, 5, and then hit the log button, and then hit the negative button, basically. So one of those two ways. And if you did either of those two ways on your screen, you should see the number 5 probably staring at you. Hopefully it does. All right. So when we report this as our pH, should we record 5, 5.0, 5.00, 5.0000000? That feels like a lot of zeros. I'm just gonna get rid of that one. Which one should it be? The second one? Everybody agree? It actually should be the last one. So it should be this one here. And the reason for that is if we look at the concentration, this has 2 significant figures. 2 significant figures doesn't mean 2 significant figures on your answer here for pH, but it means 2 decimal places. So that's why we would take it to 2 decimal places in this case. By the way, like I said, we will talk about going the other way, going from pH back to H plus, and you would do the same thing if you had 2 decimal places in your pH. Your significant figures in your concentration should be 2. So it's again significant figures to decimal places, and again going the opposite way, decimal places back to significant figures. Any questions on that? By the way, this would be acidic, basic, neutral. This one would be. It's less than 7. Should be acidic. By the way, when you are asked that question, there is only one answer. It cannot be acidic and basic together, although I've seen many exams in my day that have that answer. I've never seen anybody really go with all 3, acidic, basic, and neutral at once. So it should only be one answer if you're asked that question. It can't be all 3. It can't be 2 of the 3. It should just be one. That should be the right answer. I'll explain why in a second, why people might give both answers. Yeah. Are you asking if the concentration was of H plus or the answer? If you somehow got a pH that low of 0.05 and you started with 2 sig figs, that would be correct. It would go to that decimal point. Yeah. Questions? Yeah. All right. So let's try some here. You got an H plus concentration and an OH minus concentration. We're looking for the pH of each of these solutions. Okay, let's take a look. So on the first one here, we're looking for a pH, and again, pH is equal to negative log of the H plus. We do have the H plus given to us, so we'll just go right in. And again, obviously punch it in correctly here. And if we do that, minus the log 2.1, making sure you use our exponent button and our negative, going to get us a 4.68 pH. Once again, 2 significant figures gives me, again, 2 decimal places here. Yeah. Acidic, basic, neutral on this one. This one is This one is also going to be acidic as it's less than 7, right? Now for number 2 here, we are calculating the pH minus the log of the H plus. It does tell you in the name what you need, and that is not what we have. We have the OH minus here, which means we can go back using our KW relationship, and the H plus concentration will equal 1 times 10 to the minus 14 divided by our OH minus concentration. And that's going to get us there. We'll call it 1.7 times 10 to the minus 7 molar. Now that I have that, I could go into here minus the log of 1.7 times 10 to the minus 7. That's going to give me a 6.77, I believe, in terms of my pH. That would be slightly acidic in this case, a little less than 7 there. So it would be slightly acidic. Now, if you just rolled right into the equation here, minus the log of 5.9 times 10 to the minus 8, and you got 7.23. You obviously did not calculate pH, but you calculated our friend POH, which is not necessarily a bad thing, because there is a nice relationship that if you take the pH plus the POH, you get 14, which means if you want the pH, it would be 14 minus the POH, which would be 14 minus 6.77. Actually, 7.23 would be a better number there. 7.23 will give us our pH of 6.77. So just a few slides ahead. Also tells you what it is. POH means you need the OH minus concentration. It's calculated very similar, obviously identical, basically almost to the pH. Any questions on that there? All right. So the pH scale is based on a log of 10. So as the pH changes by a factor of 1, goes from like a pH of 3 to pH of 4 to pH of 5, the concentration of H plus changes accordingly by a factor of 10. So a pH of 3 is 1 times 10 to the minus 3, pH of 4, 1 times 10 to the minus 4, and so forth. As the concentration of H plus increases, we know that the concentration of OH minus decreases, and we will see the pH come down. And if the concentration of H plus goes down, that means the OH minus concentration will go up, and we will see a more basic pH because we have more OH minus than H plus in H. More acidic it is, and more basic it is, which means you have more free floating OH minus than you do H plus in that case. Any questions on that there? Wait, your pH, you can use a pH meter, which is a good way. It just kind of spits you out the pH right there. You put the probe into solution. It measures the amount of H plus that's basically in the solution. Truthfully, the way it works is you take a solution that you call a pH of 4, 7, and 10, and you put your pH meter in each of those, and it measures the voltage basically that's happening there. Makes a little calibration curve of the voltage and all that. Then when you put it in your solution, it goes, that voltage is like a pH of like 3.25, and it'll give you basically what's happening there. But it's a really good way to get a pretty exact one. You'll do this today in lab. You'll pH for kind of like sometimes pull test strips, you kind of mix it in there and it changes color. You try to, but idea here, you touch the solution on the paper, it changes color, try to look at the scale and see, is it a pH of 1, 2, 3, 4? You see this number type of deal, not probably as accurate as well. We also use litmus paper. It doesn't really give you pH, but a lot of times when we're using acid and bases, we use litmus paper. And if your litmus paper again turns red, it means that that solution is acidic. And if your litmus paper turns blue, that means that it is basic in this particular case. Again, litmus paper will not tell you pH or anything like that, but it will give you whether or not the solution will be acidic or basic. And they have neutral litmus paper as well, but basically acidic or basic. You'll do that as well today. I think it'll take some test it acidic or basic. Any questions on that there? pH scale, and as we talked about, we have some sodium hydroxide, which is a strong base up there around 14. We have hydrochloric acid, which is a strong acid, which is around 0. And we have pure water, by the way, which is a pH of 7. By the way, if you do not have pure water and you have water that's not really pure, maybe been out a while, will the pH be 7? pH will not be 7, it'll actually be like, in that range there, as it will pick up some CO2 from the air, make a little carbonic acid, increase the H plus concentration, and actually lower the pH a lot. So sometimes people measure it and they go, my water bad or something, and there's like, not 7 and stuff like that. So you can fix it a lot of times by boiling the water, get rid of the CO2, and it'll bring the pH back up to more closer to 7 in that particular case. As we touched upon that last example, there are obviously similar scales to pH, and POH is a very popular one, which is calculated the same way. So if we put our pH equation there together, minus the log of the H plus concentration. And once again, that relationship between the two, if you add them together, they do equal 14. This does give you a variety of ways you could solve some of these problems. You could also obviously use our KW that we've been using. Now you can, in addition, when we talk about going from pH, for example, you have the pH value given to you, you could directly calculate the H plus concentration. And the way you could directly calculate the H plus concentration is the inverse log of the negative pH. On most people's calculators, when they do inverse log, they usually will pop up a 10 and a caret and a negative pH. You could also, if you have the POH, directly get from it the OH minus concentration. The good news is it is the same calculation, basically, the inverse log of the minus POH. On most people's calculators, to get to the inverse log, usually it's the top left corner, second button, or shift button. And then usually right on top of your log button is like a 10 and a caret or a 10 and an X. So basically, if you have a display calculator, you would punch it in. For example, you would hit your second or shift button, you would hit your log button, you would hit your negative button, and then punch in, obviously, your pH or POH. If you have a non-display calculator, you will start with the number. You will then hit the second button or shift. You would then hit the log button, and then no, you would actually do negative first. So, I'm sorry. You would, before you hit those buttons, you would hit your number and then make it negative, which is really important. So you would make it negative and then hit the second and then hit the log. So on display, that's the way that you should go. As you go from pH or POH to the H plus or OH minus concentration, we do want to follow the same rules. Figures as you kind of go backwards. This is all place when we talk about POH that people screw up, and they answer that question both ways because they calculate the pH and go, it's above 7, so it's basic. And then they calculate the POH and go, cool, 7 is acidic. And before you know it, it's acidic and basic together, which it should not be. So most people in their head have the pH scale in their head, which is what we saw earlier, 0, 7, 14, basic, acidic, neutral. POH actually runs opposite, 0, 7, 14. Below 7 is actually basic. Above 7 is acidic. and it still is neutral at 7. So it does run opposite of each other. So if you have a high pH, you will have a low POH and vice versa. So because most people have this scale in their head, that is the one you should probably look at to determine if it's basic or neutral, the actual pH value. And again, just one answer when you have that question now. Any questions on that there? All right, let's try our calculators. Let's just do like everything. Why not? So on this first one, what is the OH minus concentration? What's the pH? What's the POH? And is it acidic, basic, or neutral? For the second one, what is the H plus concentration, the pH, the POH, and is it acidic, basic, or neutral? All right, so take your calculators out for a test drive, see how it goes. So. Okay, so let's take a look, see how you're doing. We'll start with the first one. Since we're looking for everything, we have the H plus given to us, which means right from the H plus, we have two options. We can go right in and get our pH. We also could use KW and get the OH minus concentration. So it really is your choice, whichever way you kind of want to do it. I'm going to roll with the pH first. So my pH here is going to be negative log of my H plus concentration. And that's going to get me a pH in this case of 8.44. Now that I have the pH, I could also pretty easily use the relationship here that if you add the pH and the POH together equals 14. So I could very easily get my POH from that by just subtracting 14 from it. And we'll take 14 minus 8.44. That's going to give us a 5.56. At this point, I again have two options to get to the OH minus. Since I do now have the POH, I could use the new equation we just talked about. I could still use KW to do it. So if I use the sort of new equation there, the OH minus concentration would equal the inverse log of the negative POH. Once again, on your calculator, something like this it will look. And that will get you, if you put it negative would be helpful as well, 5.56. That's going to get me a 2.8 times 10 to the minus 6 molar as the concentration, 2 decimal places, 2 significant figures here. You also, if you wanted to, could still roll with the KW equation and pop that in there. And that really should get you the same answer if you wanted to take that route as well. Any questions on any of that there? Acidic, basic, neutral. This one's going to be basic. And again, we want to look at the pH to help us determine that. It's above 7, not both. Yes. Any questions on any of those there? Taking a look at the other one in there, which was the OH minus concentration. So we can again get the POH from that. We also again could use KW and get the H plus. I'm going to go POH here first. So POH is going to equal negative log of the OH minus concentration. That's going to give me negative log of 9.2 times 10 to the minus 2. That's going to get me there. 1.04. I then could use that the pH should be 14 minus the POH. That's going to be 14 minus 1.04. Going to be a 1296 here on the pH. Now that I do have the pH, I could also do the same calculation I just did and get the H plus concentration, the inverse log of the negative pH. Again, going to look something like this. And that will get me 1.1 times 10 to the minus 13 molar. And you can also, again, still use KW if you wanted to. And again, would give you pretty much the same answer. if you went that way. Here again, we're going to look at the pH, and we do see it's above 7, which means, again, this guy should be basic. Any questions on any of those there? Again, going backwards here, 2 decimal places, 2 significant figures coming that way. Yeah. Yeah. Let's try a few more here just to make sure. If you have the pH is 5.67, let's also do it all here. What would be the POH? What would be the H plus concentration, OH minus concentration, and is it acidic? All right, so I'm going to start with POH here, since that was originally what was asked for. The easiest way to get there is to take 14 minus the pH, since we already have the pH given to us, 5.67. And that's going to get us 833 in this case. Now that we have both of those, we again can take our H plus, which would equal the inverse log of the negative pH. So that again is going to look something like that on your calculator when you punch it in correctly. And we will end up with, looks like 2.1 times 10 to the minus 6 molar. And lastly, our OH minus, we can again use KW if we wanted to. We could also do the same calculation using the POH. So that's going to get us here 4.7 times 10 to the minus 9 molar. And once again here, this would be the pH, which is less than 7, which means we would expect this guy to be acidic. Yeah. Any questions on any of those there? We'll just do what it asks here. So, all right, so this is our H plus, and obviously our only choice in this case, since that's the only number we got, inverse log of negative pH. And again, you do want to make sure you do make it negative here, and we will end up here. Looks like 7.2 times 10 to the minus 4 molar. And again, I may not give it to you in scientific notation, but 2 decimal places, 2 significant figures. Any questions on calculating H plus, OH minus, pH, POH? Need to be able to obviously do all that. I think most people usually struggle with how to punch it in. So make sure you got clear as to sort of what calculation, how you punch it in for what you're trying to do. So up until this point, we sort of talked about what is the pH, POH, and all that stuff of kind of generic things like H plus and OH minus. But how do we get the pH of a strong acid or even a strong base? Well, because pH is minus the log of the H plus concentration, that's going to be really important in terms of figuring out the pH of a solution. Remember that we do have a list of some strong acids that we talked about. Again, hydrochloric, nitric, perchloric, sulfuric, hydrobromic, hydroiodic. Remember, some of our strong bases is group 1 and 2 on the periodic table: sodium hydroxide, potassium hydroxide, calcium hydroxide. Go down, strontium, barium hydroxide, etc. Also lithium hydroxide. So when we do have strong acids or even strong bases, like HCl, for example, it will 100% break apart into H plus and Cl minus. Clearly, in terms of pH, that is the most important thing that we want to figure out. So if we know the concentration of the whole thing, like we have down there, 0.1 molar, we do know it is a 1-to-1 relationship between the whole thing and the H plus, which means in this case, we would take 1 times 0.1 molar, and that's going to give us 0.1 molar as our H plus concentration. And that really is all we would need to calculate our pH. We could go minus the log of 0.1 molar, also known as solution number 1 in your lab today, by the way. Yes, it is this right here, a pH of 1.00, which is acidic, and what we would expect. Now, if you had something like a strong base, it works the same way. It's going to 100% break apart into a sodium ion and a hydroxide ion. In this case, is a little bit different. We would want to use the whole concentration to get to our hydroxide concentration. But remember, that's going to give us not the pH, but the POH. Then you need to subtract your 14 to get to the pH. So there's a couple extra steps, or an extra step that you have to do. Because it's a base, you first would probably get the POH. And like I said, the easiest move would be to take 14 minus that to get yourself to the pH at that point. Any questions on that there? All right, so why don't you try a couple here? These are both strong acid and a strong base. We're looking for the pH of each of these solutions, so see what you come up. Let's take a look. So obviously this is going to be a strong acid, which means this perchloric acid will 100% break apart into H plus and perchlorate here. In terms of the pH, the important part is the H plus concentration, which it is a 1-to-1 relationship here. 0.025 would be my H plus concentration, which is all I will now need to go into my pH equation. And that will yield me a pH here of 0.025, 1.60. That is acidic, and that makes sense since this is an acid. Any questions on that one? This is a strong base, which means when it breaks apart, we will get a calcium ion, and we actually will get 2 hydroxide ions. Remember, with a base, it is the hydroxide that's the important thing. And if this is 0.025 molar, it's a 1-to-2 relationship, which means, as we talked about with concentrations, you actually need to multiply the concentration by 2 to get the proper concentration. So that's going to be 0.025 times 2, going to give us 0.05 molar. That will go into, once again, our POH, as that's the OH minus concentration. It's going to give us a POH of 1.30, and then take in our 14 minus our 1.30. Give us a 1270 pH, which is good because that is basic in this case. So if you are actually given a formula of a acid or base in this class, the good news is you could assume that it's probably going to be strong. And that's because if you wanted to calculate the weak acid or weak base pH, you should wait until you go to Chem 1B and do it. Yes, it's a much bigger calculation. So any acid or bases you come across probably in here should be strong. The good news is most strong acids are monoprotic, which means the H plus concentration is going to be the same as the concentration of the acid. Really, with the bases like we have here, is probably the only ones you might have to worry about adjusting the concentration. Any questions on that there? All right, so that leaves us buffers. So we're going to talk about buffers and what they are, how they work, and we'll give it a go. So a buffer solution is a solution that resists changes in pH, even if you add more acid or base to that solution. So a misconception that people have about a buffer is it is a neutral solution, and that is not necessarily true. You can have a buffer that is neutral. You could also have a buffer that is acidic. You could also have a buffer that is basic. You can make a buffer at any pH that you like. So whatever pH you want to make it, you could actually make a buffer at any pH. What that means, for example, if we had a solution that had a pH of 5, for example, if we took that solution and added more acid to it and it was a buffer, we would expect the pH to still remain around 5. We wouldn't expect the pH to go from 5 to like a pH of 1, a really big drop in pH. It will move a little bit. So maybe it'll go from 5 and you add some acid, maybe it goes 4.9 or something like that, but a very small change down, but it will not have a really big change. And if we had that same buffer and we added base to it, we would expect the pH to basically stay around 5. Once again, it will go up a little bit. Maybe it goes to like 5.1 or something like that, but it will not go from a really big jump of 5 to like a pH of 12. So you won't see that really big jump. The reason it's able to do that is actually what is a buffer is made out of. And a buffer is made out of one of two combinations. It could be a weak acid or the salts of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. What does that relationship mean? That is the Bronsted-Lowry definition. Those two things are basically related to each other by 1 H plus difference. You cannot have a buffer that's made out of a strong acid or a strong base. So there's no way for you to have a buffer and go, this is my buffer, and it's made out of a strong acid or a strong base. It has to be a weak acid or weak base because those guys are weak electrolytes, which means they're going to stay together. And the important part of how a buffer works is when you have the beaker of your buffer, you're able to keep the acid part of your buffer in the solution and the base part of your buffer in the solution. So for example, we'll do a different buffer than everybody likes to choose, which is acetic acid and sodium acetate like you will do in lab. But let's just say we made a buffer out of these two things. So this is hydrofluoric acid, which is a weak acid. This is the salt of its conjugate base. It's really called the salt of its conjugate base because there's a sodium. But in the aspect of the buffer, it's really the F minus. That's the important part. So those two things that I just circled are really the buffer parts. And because HF is a weak acid, when you put it in there, along with a little bit of sodium fluoride, it will set up this equilibrium equations and all now of this. And basically, as I just mentioned, you will have this guy in the solution, which is the base part of your buffer. You will have this guy in solution, which is the acid part of your buffer. And that is extremely important for how this buffer is able to actually work. Now, if you try to make a buffer out of HCl and say sodium chloride, which is basically HCl and Cl minus. So that is a strong acid and its conjugate base. Because HCl is a strong acid, when you put it into your beaker, you're not going to get any HCl units still there. You're just going to get H plus and Cl minus, which means in your strong acid conjugate base pair, you only have a base part of the buffer. You wouldn't have the acid part, which is really crucial for it to work. So that is why you cannot make a buffer out of a strong acid or strong base. It has to be made out of something that's weak because it'll set up this equilibrium that allows you to keep in solution the acid part of the buffer and the base part of the buffer. So that's really critical for how it works. The reason we add sodium fluoride, because it is a source of fluoride. So it kind of beefs up this amount for your buffer. So you have a good amount of that in the solution, along with a good amount of your acid part in the solution. So let's take a look at how this works in a buffer and a non-buffer situation. Let's start with water like you will do today. And water is a non-buffer, not a buffer. So if I have a beaker of water there, like you might have today, you're going to take some hydrochloric acid and you're going to add this to it. And when we add hydrochloric acid to water, it will 100% break apart into H plus and Cl minus. Which means what you just did to this water is you just dumped in there a bunch of H pluses and some Cl minuses. Not that important to Cl minuses, but you just added a bunch of H plus really quickly to that solution. You have none of the HCl units still together. That means that the concentration of my H plus went up a lot. That means my pH should probably go down a lot. So your water, let's just say you had neutral water at 7, would go from a pH of 7 maybe down to a pH of 2 or 1, a really big jump in pH because you basically just flooded the water with a bunch of H pluses, which is why it's not a buffer, right? Because it just changed pH by a lot. Now, if you took sodium hydroxide and added it to water, which once again is not a buffer either. You would have sodium ions and hydroxide ions. So if you took your water here and you added your sodium hydroxide, you're going to add a bunch of sodiums, which is not that important for the pH, won't really do much. But what it will do is add a lot of hydroxide really quickly. So you will have 100% of these guys in that water. You have made a lot of free H plus in the first one, but a lot of free OH minus in this case. And that means that the concentration of OH minus will actually go up. And if you remember, OH minus and H plus are tied to each other, which means if my OH minus shoots up, my H plus concentration will go down a lot. And the result of that is your pH will go up a lot. And we would see, for example, go from a pH of 7 to like a pH of 10 or 11, a really big jump in pH because you just influxed in there a lot of hydroxide concentration, and that makes the H plus concentration drop, and the pH will then go up by a lot. Any questions on that? So that's what's going to happen today when you add your 1 drop, and you'll see the color change happen really quickly. Now let's talk about what happens when you add it to a buffer, and we'll use this one as an example. This is the acid part of my buffer. This is the base part of my buffer. And when I have that in solution, as I mentioned before, they are both in there to start with. So once again, we have the acid part and the base part of our buffer to begin with. Now, if we take that same HCl that we want to add, that's a source of H plus and Cl minus. When I add my HCl to my buffer, it's actually going to react with one part of my buffer. So HCl is an acid. Should it react with the acid part of the buffer or the base part of the buffer? They're called acid, what type of reactions? Acid base reactions. So when you add the acid to your buffer, because there's an acid part and a base part to your buffer, it will actually react with the base part of your buffer, and it will do a double displacement reaction and actually produce HF and sodium chloride in this case. So they'll switch partners basically. So what we produced is, in this case, actually part of the buffer, which is what always happens. So when you have a buffer that has both of those parts, an acid part and a base part, and you add acid to it, it will use some of the base part up and it will make some of the acid part, which is what we have here. We have sodium chloride, which is actually a neutral salt, and that's neutral, which will not actually affect the pH. It's actually what we do not see here that we did see when we added this HCl to water. What did we see when we added HCl to water that we do not see here? That's important for pH. It is the H plus. So when we added the HCl to water, we made a ton of H plus really quickly. When we add this to the buffer, that H plus that's coming in is going to go find the fluoride, and then it's going to make some more of that HF. We will not produce any more free H plus. So we do not see any free H plus being made. And what that means is the concentration of H plus will stay relatively constant, whatever concentration you had to start with. And that means your pH will stay relatively constant as well. It will go down a little bit, but you will not see a really big jump because you didn't just influx a ton of H plus into the solution really quickly. And it basically gets tied up in making HF in this case. Question on that. So what happens when we add our sodium hydroxide to this same buffer? So if we added our sodium hydroxide to this buffer, once again, we have our buffer set up to begin with. We have our acid part, we have our base part in there. We add our sodium hydroxide, which is a source of sodium and hydroxide ions. Sodium hydroxide is a strong base, which means it's going to react with the acid part of your buffer. And it will do an acid-base reaction, also double displacement. You're going to switch partners. We're going to get some sodium fluoride, which was part of the buffer to begin with. And we will make water, which is not going to screw up the pH, right? It again is what we do not see here that we did see when we added that to water. What do we not see here that we saw when we added the sodium hydroxide to water? There is no free There's no free OH minuses, right? When we added that to water, we had a bunch of free OH minuses that entered the solution, as we see here, right? A bunch of free OH minuses went into that solution. In this case, when our OH minus goes in, it actually will react with this guy, and it will actually offshoot water, which is not going to affect the pH of that solution. We don't get the free OH minus floating around. And because of that, the OH minus concentration stays relatively constant. And because the H plus concentration is related to that, it also stays relatively constant. And that keeps your pH relatively constant as well. Again, if you're following the pH, you will see it go up a little bit, but will not have this really big jump in pH because it is not allowing the OH minus into the solution. So the way a buffer really works is because it has an acid part and because it has a base part that has to be in the solution to begin with. When you add additional acid or additional base to your buffer, it prevents the formation of free H plus or free OH minus in the solution. And because you don't add a ton of that freely in the solution, the amount that was there to begin with in terms of the H plus will stay relatively constant and the pH will stay relatively constant as well. Any questions on that there? Now, just one last point here before I let you go, which is if you had a buffer, you typically would make maybe about the same amount of your acid part and your base part. And when you add, for example, some acid to your buffer, it will react with the base part, but as we saw, you will make more of your acid part of your buffer. Dramatically drawn here. And the same thing happens when you add base. It will react with the acid part of the buffer and make more of the base part of your buffer. Now, there is what is sometimes referred to as buffer capacity, which means there's a limit to how good your buffer will be. What happens if I didn't pay attention? I just kept adding acid. Every time I add acid, I'm using up some of the base part of the buffer, right? So if I keep adding it or I add a really strong amount of acid, I'm going to blow right through the base part of the buffer. And at some point, it will no longer be a buffer. And if I keep adding acid, I will just be adding H plus, and you will see a really big jump in pH. So buffers only work under specific conditions of how much concentration you're adding. The molarity of your buffer is really important. So you can make a really good buffer, or you can make a really crappy buffer that really won't resist too much change. The idea is to make one that obviously can resist change over a good period of time, and you sort of regenerate your buffer as you add acid or base to it. Any questions on buffers there? All right, we will lay it up there.